So let me go, medias res. First of all, Brownian motion is of course known because Robert Brown did this experiment using actually this microscope of Leeuwenhoek. And actually there was it was a big debate later on, did he really see Brownian motion? But of course that instrument is actually kept safe in the Linnean Society, and it has been repeated, and actually it worked. Thanks to, because that experiment was rather simple, this instrument, but it was excellent. And of course there were precursors like of Ingenhus, but of course when it was more to turbulence or to evaporation. So he was in that sense first. But there's a strange story, because I must say Brownian motion, in my opinion, a person who has been overlooked really is William Sutherland, because he actually has written a paper in 1904 and 1905, republished the same paper in Phil Mack. He was actually an Englishman going to Australia, and there was a conference in Dunedin in New Zealand, and he had a conference report, which I will make a comment on, where he derived this Einstein relation. And it was long before Einstein. Now, Einstein, of course, also derived that in his 1905 paper, but actually this second paper appeared even 4 months before. And then from Abraham Pais, that actually was guys in the Olympia in Bern, actually read the Phil Mack papers of this person Sutherland, because Einstein always said, come guys, like Habeck, Grossman and Michele Besso, we have to read those papers. And actually, it's in German, the Einstein paper, and the arguments are identical, almost word by word, from the paper by Sutherland. So this is, in some sense, a plagiarism, one of the first I actually discovered. But before I got actually insulted in the year of Einstein, 2005, by many friends from Israel and otherwise. But Einstein has also derived that, but of course he was the first one who actually told the people you don't have to look at the velocity, but you have to look at the distance. And in addition, he actually had the first Fokker-Planck equation, also did the equation, so to speak, the free diffusion equation in that paper, which is of course central, okay? And after, this is another nice story, Smolichowski, I also got the Smolichowski Prize, actually saw this paper, but of course at that time, he said that we are not allowed to publish papers in theory only, but we have to do experiments. And when he saw, this is one of the first theory papers, Einstein, when he said, okay, now after you publish only theories, I'm also allowed to publish. And then he published his famous paper in 1906. And this is now the paper by Sutherland, where he essentially balanced the osmotic pressure with Stokes' law. And actually, he did it even for sticking condition or slipping, full slip and full stick. And then he has here even a correction to the C with the beta factor. And this is actually the paper there. And he had, and that's why it was very important, because he could now determine the mass of the molecules. At that time, it was a big debate about that. And correcting the record, so the Australian people were quite unhappy, but where is actually, you find all these papers, also the original papers of Dunedin, which I had to wait for almost 30 years to get the paper from my conference proceedings. You find it actually on my homepage, where I have a homepage entitled 100 Years of Brownian Motion, Historical Items, and you find there a whole series of all these original papers. But it took me a really hard work to get this. So, Brownian motion is, of course, used nowadays in almost universal in chemistry, in all these fields which I list here. Biology, you can read it, and etc. Chemistry also in astrophysics, high energy, and also quantum mechanics, of course. And Brownian motion really plays an almost essential role in all areas of physics. And of course, you have to make many models. These fields all have many, many models of Brownian motion. But now I recall this famous guy, which I forgot the name. But remember, all models are wrong. Some are useful in order to make you more happy. Many actually are useful, but they have always a limited regime of validity. Because you all know free Brownian motion. Everybody knows here that it's a Gaussian, right? It's a spread. Okay, it's clear. But it's when I was a student, I already interrupted. The guy said, this must be wrong because a Gaussian has tails from minus infinity to plus infinity. So at any finite time, there are particles you find way beyond the speed of light in a fixed time, okay? So it must be wrong. And this was actually, I'm a bit proud. I had a guy with Jörn Dunkel, is actually one of my most famous students. He got actually a full professorship at 36 at MIT. And we did then relativistic thermodynamics and relativistic Brownian motion in his thesis. And we corrected all that because even the models were usually are sort of like wave equation-like, so telegraphic equations, which are also wrong. But if I have time, I show you some slides later on. Now, another thing is, which is now important, which I always wonder why you guys have all these models, because I have always a concern of making models. You know why? Because you have data, and data are stochastic. And when at some point you make a model, you have to actually to make a model, but sometimes we know only the mean value, it's like the drift, okay? And then what is the correct noise? Is it a Markov process which you are actually looking at, or is it a non-Markov process, which is an infinite large class, you know, to make a model? And so actually, in some sense, it's a tough job, actually, and that's why I published once a quantifier, which distinguishes nicely between Markov and non-Markov. Unfortunately, that paper is not cited over 100 times, but only about 70 times. But if you look at mean first passage time, higher moments, we would easily check from your data if it's a Markov process behind or a non-Markov process. I would like to advertise that for those who have not read my paper. And then another thing which I did was actually using the issue of stochastic interpretation of the so-called increments of the Wiener noise. And in my thesis of when was it, long time ago, 1972 or so, and I actually generalized this Ito integral, which essentially gives you different noise-induced drifts. And so to speak, you probably know about the Ito interpretation, which is lambda equals 1, where all of this goes away here, with 1 minus 1 is when 0, and so on. And you have here a 1. That is actually a nice martingale property. That's why the mathematician constantly use only martingale Ito. And Satonovich used this half. I met Satonovich also personally, and because the differentiation rules go a little bit with the lambda half Satonovich interpretation. And I say the pause point is also a good one, and you see why in the next page. Because this is actually also was a big debate. You see, that's where physics comes in. Imagine you have a bath and you have a linear capacitor, and you have a nonlinear resistance. Okay, then of course you have charge fluctuations on the capacitance, right? And then of course this was once people did some work on this and said, oh, this is good, we can have used Brownian motion, and then we have a voltage there and we make them with series, tack, 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 you know. But of course, you know, thermodynamics tells you that the voltage, you cannot get a voltage on average because it must be symmetric. Q squared over 2c is 0, so to speak, right? The average then. So you don't have a finite voltage, so it will not work. And then, of course, you ask, how do you do now a model for this nonlinear resistance? And you know, you have a conversation of charge, and you make the probabilities. The physics tells you have a current, and you have a probability, and the P dot is obviously given by the drift term. And then you have here this nonlinear resistance, and that's now the difference, because we know from Fick's law or the Fourier law that if you have a nonlinear resistance, it has to go here, and you see from this Fokker-Planck equation, so to speak, the derivative of dDq is between the multiplicative noise strength and this part, okay? And so if you want to get, so in the Ito interpretation, if you just say, oh, we take Ito here, you would miss out with the red term, you get no Gaussian. If you use Ratonovich, you get no Gaussian. You have also this term. But in the Hänggi interpretation, actually, you get here the deterministic drift, and using now this pause point, so to speak, interpretation, you get precisely this Fokker-Planck equation. Of course, all of this different interpretation can give you the right physics. So the physics is determined by the correct equation, but you have to actually adapt. So this is the big problem, you know, when you have not additive noise, how to actually correct when you actually want to make a model. So this whole is really still not totally always present in all kinds of modeling. And in thermodynamics, we know that you have to obey the thermodynamic laws. That's why you have a test case. Now I actually will go to non-equilibrium and I say something about stochastic resonance, which I'm quite proud of this area, and Brownian motors, which I did, as he already said. And stochastic resonance in a nutshell is essentially the amplification of weak signals in presence of noise, and you get more signal out, which is a bit paradoxal. So if you have a noise source and a weak signal, actually noise helps. And I don't want to go into it. I come back to that essentially is the escape time, which is the Kramer's time. You have, of course, two escapes to the right, to the left. So usually get a resonance, so to speak. So this is a picture of a signal. And if you have very weak noise, you have here random motion, but you get the stochastic synchronization, a stochastic synchronization now, where essentially when this escape time is half of the driving period. You can see this nicely here, so to speak. Okay. And actually the spectrum, this whole field of stochastic resonance was really giving a strong push of doing stochastic process with explicit time dependence. Because there's little work done before this area of stochastic resonance where you have explicit time dependent Fokker-Planck equation with periodic signal or with aperiodic signals. And because you have now time inhomogeneous processes, which are not time translation invariant. And what is very nice, this was the first application of it, if such a spectrum, if everything is symmetric, you can show from the Floquet theory now that you get only spikes in the autocorrelation, the spectral density, this autocorrelation function of such a process, map averaged over the driving period, has only sharp delta spikes if it's at odd multiples. 1, 3, 5, 7. And in any asymmetries, as small as it is, will immediately show up with a structure here, a 2 omega and 4 omega, for example. So this is a very good detection device. So it has applications. And because of this, it took off stochastic resonance. So we have as measured signal to noise, the spectral amplification, so to speak, and offer the area under the recurrence times and things like that. This is that famous review here on stochastic resonance. But I want essentially to show that with, so to speak, the weight of that spectral function is essentially given more noise, more signal. And it's not so much for the people, the engineers, it's not so much important to hear the highest peak, but this is best amplification. But it, of course, here is the gain. A small change in noise gives you big gain in the detection. So, and this essentially, you can, with a simple linear response theory, you have here the weight of this peak, and when the intensity goes as a square, which is 1 over the diffusion strength times the Kramer's time, so to speak. So this is a function which for small t is large, and for small t this goes to 0, and for large t this goes to 0. But yeah, for large d, this one is, so to speak, a constant. If d goes to, if d is very, yeah, so it goes, essentially has this exponential decay. Okay, so why is this a rougher universal system? Because you need somehow a threshold, like a barrier, or somehow of a threshold, you need a weak signal, and you have the presence of noise. And this, of course, implies almost for sure anomalous amplification properties. And one of which I am actually also, it has taken off since when we started with, since I don't know when we had the start paper of Wiesenfeld and so on in the early 80s. And now you see, for example, we talk about climate. There's a nice work by the Max Planck Institute in where is it? Stefan Ramsdorff is in Nottingham in, what's the city called, where anyhow, the Max Planck Institute outside Berlin, and he has actually done simulations for the ice ages, so to speak, and he finds if we have only noise, if he makes in his models, climate models with very weak noise, he gets with curves over here. But if he adds somewhat a signal, a weak signal, he finds here such peaks which repeatedly go between 1,500, 3,000, 4,500, and when enough for 6,000. So we get here a cycle, so to speak, periodic cycles, which are known, observed in the Greenland Ice Project, which have a period of 1,500 years. And this Greenland Ice Project has a data series of 110 years. And you find always after 100,000 years, so two warming periods are essentially separated by 1,470 years. So don't be so afraid of the climate change. If you just live long enough, now we are in a warming phase, it will become for surely colder, because this is a long series which we have. The question now is in this whole field, where is this 1,000 years coming from? Nobody knows. It's certainly not of Earth origin. It's not, it has nothing to do with the moon. It must be out of space, okay, as a cosmology problem. Another big thing which I'm very proud to say is about, of course, it took off in the medical sciences, because you have firing neurons, which essentially, if you have a signal and have noise and you cross threshold, the brain starts to work and gives you a thing. So you get here interspike diagrams, and which are essentially related to stochastic resonance. And the simple experiment is you see this cube, now you focus on the lower surface or you focus on the higher surface when you get such a spectrum. But now if I help you, and if I do here, so to speak, a movement, if I would do a little bit, if I help here with this laser pointer to go between this, when you get total different structures, if you take all the students here at ETH and they tell you, I see now bottom, I see now top, and so on. So this is stochastic resonance in the brain, so to speak. And here, this picture is quite important because the group in Boston, Jim Collins, he found out what actually has made, it's now a Swiss industry even, which a company which has invented, so to speak, including also the Boston people, stochastic resonance therapy. What is it? Actually, they have had humans, especially older people, which have a hard way standing on one foot for a long time. There's this sway problem. Human motility, you start to shake, so to speak, right? You are not so young people can stand long time on one foot and things like that. So you have a motility. So motility balance becomes a problem in old age. And now they actually put with people, they have a vibratory signal, which can be even mechanical or even electrical, and they find a huge improvement in stability. And I had now I had a student in my team in Augsburg who had a heart disease. He had to take a strange drug, and after that drug, he could not stand for a long time on his feet, okay? Had to somehow with bicycle thing and so on. And when actually we told him, let's try SRT, at that time I already had with stochastic resonance therapy, which you find now everywhere in the centers, in the doctor centers or rehabilitation centers. And he did this for 2 months, and actually he knocks around, no problems anymore. And actually in this paper I showed you, they proved that actually with people which stand, older people, say 89, 84 people, feel with stability back like a young man or a young woman. So that's why I show these pictures. If you come to this age, go on with vibrating plates with stochastic noise, and then you go back in age, formally at least. Okay, the next topic is now what you mentioned, with Brownian motor stuff. And essentially, you see if you have such a zigzag potential and you switch off that profile, you have free diffusion if it's flat. But now you see that you have different distances. Here you have to move a small distance diffusive length. Here you have a long, but because it's the periodic potential, the mean force is 0. And now what you find is after you switch on, switch off, which is a non-equilibrium problem because it's not time independent, you switch on, off with zigzag stuff. And then, of course, you can actually get motions. And you get new pumps, you get non-equilibrium phenomena. I think I have a patent on this with the Max Planck Society. You have actually, I have two patents just for one I did with the Navy in San Diego, which can differentiate with stochastic resonance between Russian submarines and US submarines. And the second patent with people from the Max Planck Institute for Microphysics, the physics is something nice because we did a hydrodynamic approach. We took such a ratchet profile, which were about 10 millions per square meter. We have pores like that. We have here pores which has a shape. And when we pump water through, and when we see how those particles move between, for example, infected cells and non-infected cells. So here we have the picture of this experiment, which is patented. And when you find that drift, no drift, there's no oscillation with the fluid, you get no motion with the pump on. Periodically, you get here, of course, with separation in size. And now that is very nice. The main point is that if you do with experiments and pump here sinusoidally, you get different parameters, also infected cells versus non-infected cells, where you go this direction, the other ones go in the other direction. No, what I like about it, no chemistry involved right here, no expensive drugs from Novartis and things like that. Just pumping fluids. Okay, my time is over, but I have more to say about things I do not understand. And because there are so many smart people, let me tell you a little bit why I die before some of these questions are solved. So generations of Brownian motion. Of course, this is actually now a topical field, namely, so to speak, long time motion. So we have, we can use a generalized Langevin equation. And here I have a little story to tell. I mean, nowadays, so we can make motion if we have an environment, we have a system, we have an interaction, and we can, in principle, solve the Brownian motion for this problem. So we have a Hamiltonian background for such a motion. Once I gave this talk, and Peter Stauffer said, Peter, you use Hamiltonians. Hamiltonians are useless. Well, I like Hamiltonians. At least I can have exact results, and I can really do what, and I have a strong basis for it, because most of your models, you never know in what regime they are valid. And of course, here you have now a motion which can be, if its integral is the memory function, friction is constant integrated, you have normal diffusion, you can have super fast diffusion or super slow, so to speak, faster than normal and slower than normal. And of course, nowadays we have this whole issue of mean squared displacements, which you find in all kinds of biological and physiological studies. That's normal Brownian motion, but even Levy Brownian motion, which is actually Levy flights, are not normal. But if you have a super diffusive case where hundreds of models which are super diffusive, and I ask now here the experts, which one you think you should take? Because you have no Hamiltonian now. So maybe a GLE is already good enough. And this is actually a small criticism I have about this field, because you guys model. First of all, is it a Markov process? Is it behind it? Is it whatever? And what time scales is the model valid? Because you look only at, for example, the second moment. You are not sure how the fifth moment behaves with different models. And this, of course, this I don't have to say, you know it essentially, where you can have super diffusive with fat tails in the distribution of jump lengths, or you can have fat tails with the distribution of residence times. Which one? All of them fit the experiments, so to speak, over a certain finite time scale. But you don't know the mechanism behind it, because you don't have a Hamiltonian now, Mr. Stauffer, right? And it would be nice to have one. So essentially here is, I'm always a bit skeptical, because there's a whole zoo of models like Barkai and all of these people. So on. Of course, nowadays we have other interesting. I mean, active Brownian motion, I have no time to go into it, but this is now, so to speak, where the particles itself are active. But I will stop here. This is what I said with my student, with this question I had when I was a student, how you get away, so to speak, from this Gaussian here and get, so to speak, this is what you learn in school. And with this new theory here, we actually have here finite, at any time, a finite cutoff. So, and essentially, it's just a highly non-Markovian process. And you see what was around before Dunkel did with PhD on this. We had here, so to speak, wave equation, and Malzoliver and Weishaupt and many other people used this telegraphic equation because we said the relativity with electrodynamics, we know what but such things here, sharp fronts, are unphysical for any particle. Okay, because if you imagine you have a particle would have assume infinite kinetic energy. It's only a good model for photons, which have no mass, no rest mass. Anyhow, so there's a physics report which is now highly cited in this area. So you can imagine we know very little about relativistic thermodynamics. And of course, this is a one-particle theory, and you know there is no consistent two-particle theory in special relativity. So this is an open problem. In principle, you have to find a field theory, but a field theory for 10 oranges is very hard to do, right, relativistically. So this is a big open problem. I don't know how to do. Of course, we know German because I do high energy physics. I come from high energy physics. So with field theory, we can do it. But 10 oranges are not a field, right? You have really 10 oranges. Okay. So in my case, the message is noise sometimes helps.
Right. Ja, Applaus.